With the increase in the complexity of deep learning models, it's often very easy to induce memorization and high sensitivity to adversarial examples. Simple data augmentation like rotation, flip, distortion, obstruction, etc. has proven to improve generalization performance, a simple fact that adding more perspective variation of the same image makes it difficult for the model to memorize. If the augmented data is too similar to the original data, the machine learning model may overfit to the augmented data, leading to poor generalization on new unseen data. Some standard data augmentation techniques such as flipping or rotating images may not provide enough diversity in the dataset, which can limit the effectiveness of the technique. Certain data augmentation techniques may not be suitable for all types of computer vision tasks. For example, some techniques may not work well for object detection tasks where object size and position are important factors. Augmenting the data can significantly increase the computation time required for training the machine learning model. Thus, it is important to carefully select the augmentation techniques for the specific computer vision task at hand. The mix-up vicinal distribution can be understood as a form of data augmentation that encourages the model to behave linearly in between training examples. This linear behavior reduces the amount of undesirable oscillations when predicting outside the training examples. Also, linearity is a good inductive bias from the perspective of Occam's razor, since it is one of the simplest possible behaviors. Deep learning models are sensitive to adversarial examples and prone to memorizing corrupt labels. Mix-up augmentation relaxes this by combining different features with one another. Same happens for the labels too, so that a mode does not get overconfident about the relationship between the features and their labels. Mix-up is a simple and data-agnostic data augmentation routine that trains a deep learning model on convex combinations of pairs of examples and their labels. In other words, mix-up constructs virtual training examples. Throw the linear interpolation of two random examples from the training set and their labels. The lambda denotes a random variable that is independently drawn from the beta distribution for each augmented example. The mix-up hyperparameter alpha controls the strength of interpolation between feature target pairs, recovering the empirical risk minimization principle when alpha is 0. Now, let's implement the mix-up procedure. The first step in our code is to import the required classes and methods to read input images and mix them up. Now, we can visualize the cat image and dog image. Now, let's load two input images, one contain a cat, and the other contain a dog. Once the images is loaded, it is resized to required dimensions. Herein, we implement the mix-up augmentation function according to the mix-up formula. The implementation of mix-up training is straightforward and introduces a minimal computation overhead. By applying the mix-up function, we can obtain a new instance of data label pair. By mixing two images together, the model is forced to learn a more robust decision boundary that is less dependent on specific features or noise in the training data. Overall, mix-up augmentation is a powerful technique that can help improve the generalization and robustness of deep learning models due to several advantages. Mix-up is a data-agnostic data augmentation routine. Mix-up makes decision boundaries transit linearly from class to class, providing a smoother estimate of uncertainty. Mix-up reduces the memorization of corrupt labels. Mix-up increases the robustness to the adversarial examples, and also stabilizes the training of generative adversarial networks.